I'm Jeremy. I work for Google and I'm on the FHE team there. And we're working on this sort of foundation for FHE compilers. I have a whole slide about my background, so we'll get to that in a second. Um, I want to start with sort of the agenda. So I have a one slide pitch in case you have to leave. This is going to be the one summary that, if you get nothing else from this talk, you can just get this. I'll cover all of the different why questions about why we're doing this. I'll give a technical overview of some of the compiler framework details, and then I'll talk about what's specific to FHE and HEIR. And then at the end, I'll talk about some resources I'm working on to help people get involved. So the one slide pitch. Okay, here we go. We are building a compiler toolchain with all of the established ideas in FHE to accelerate FHE research and lower the barrier to production FHE. So by compiler toolchain, I mean, we are building this on top of the MLIR framework, which I'll cover in a bit more detail later. By established ideas, I mean, we are going to include every FHE scheme that is fast and, production ready. We're going to have all of the fast polynomial math involved in doing FHE applications. We're going to have every optimization we can think of, and we're going to include like formal noise modeling. By accelerating FHE research, I mean that if you are an FHE research or an academic and you're thinking about doing a project related to an FHE compiler, then we want to have a place for you to do that where you don't have to focus on compiler infrastructure and you can just focus on trying out your novel idea. And by lowering the barrier to production FHE, I mean, we are going to have benchmarking across applications and across different hardware targets. We're going to have easy integrations with different front ends like C++ and Python and TensorFlow. And so we want to really get this to be sort of ready for a company like Google, where I work, to use this on, code written by someone who's not a cryptographer. Okay, so if that pitch was enough, we have a working group that you can come to. So we have a design meeting every 2 weeks where we talk about sort of what we've been working on and what we want to do. We've got participants from across industry and academia, including Google and Intel. Zama is involved, Crypto Lab's involved. We have folks from various universities showing up. And hardware startups as well. So the question is, do you want to join us? There's the link and the information to show up. I think our next meeting is this upcoming Tuesday, I believe. Okay, so now I want to talk a little bit about the sort of why, and this is going to be like very soft, and it starts with me, right? Okay, so why do I care about FHE, right? Again, I'm Jeremy Kuhn. My whole career shtick has been like math. I did my undergrad in CS and then I switched to math. I did my PhD in math and focused on theoretical computer science. I've been writing this math blog for like 13 years. And for a lot of my career so far, it has been kind of like follow my nose to where the cool math is happening and like try to get paid to like apply cool math to software, right? Before I joined the FHE team, I was working on data center optimization in Google's data centers. So I did a lot of integer linear programming and supply chain optimization, which was sort of a cool type of applying math to software. But then as my career sort of developed, I started to have these questions like, okay, making money for Google is interesting, I guess. Putting cat videos on the internet is interesting, I guess. But how do you choose like a meaningful problem to work on, right? And what constitutes a meaningful problem? And once you think you've found a meaningful problem, what's the best way for you specifically to contribute to that problem? And then, in addition, right? How do you combine the sort of keeping your career interesting and growing as a person and growing intellectually while also leveraging the strengths that you already have to contribute to that problem in a meaningful way? You don't want to like work on a problem. If I were to work on like a nuclear reactor, I know nothing about physics, right? Like, okay, maybe I could do something there, but like I wouldn't be leveraging my strengths very well. And then the question is like, when is the right time to work on that problem? And for FHE, I think it hits like pretty much all of the sweet spots here. So I think about this as like a balancing scale. And on one side, there is like the potential for your problem to do good in the world. And on the other side, there is the potential for evil. And I think FHE has like a very good balance of potential good. Um, and then the rest of it is sort of like my personal skills and the right time. So I like applying math. I like building serious production software, and I'm good at that. And in addition to that, I'm not a compiler expert, but I'm learning compilers, and I'm finding it very pleasant. And at the same time, there's sort of this like, now is the right time for FHE, right? Like, I'm probably not going to make huge theoretical breakthroughs in cryptography theory, right? And I'm probably not going to invent a new FHE scheme from scratch. So now that we have all these nice FHE schemes, my sort of role here is to like figure out how to get these into production in a good way. And part of that is like, you know, I work for Google, and Google has a lot of power, right? And at some point, Google is going to be like buying hardware or making hardware that goes into data centers, right? And I have that background for like how to funnel some of Google's power and energy and money into doing that, right? So like I'm in like a very nice position to help the FHE community along. And then there's also like this sort of all of this interesting new hardware, and I don't know anything about hardware, but it's nice to learn. So there's like all of this sort of like on the balance side, and then there's like the other side where it's like, okay, maybe someone could figure out a way to use FHE for like not good things. And I have to deal with that, but the good outweighs the bad in all of these cases, I think. Um, so okay, so now more of the political side. Why does Google care about FHE? So in the Google landscape, this is sort of all public facing. There's a lot of increasing regulatory pressure on Google, especially from the European side. And so Google is sort of faced with a lot of situations in which either something that they're already doing they can no longer do, or they can no longer do efficiently because of increased regulation. FHE might help them continue to do that. And in other cases, there are like new product ideas that Google wants to do, but they kind of know that it's dead in the water because of privacy issues, right? And it's like, okay, how can we do this thing without violating all of the privacy regulations that we have to uphold? Um, and in addition to that, right, Google has like all of these products, right? It has like a huge market share for all of these random apps. I don't even know what some of these symbols are, but there's lots of users using them, and many of these users want privacy, and Google can offer more in some of these products. So I'll give one example. So in Gmail, right, or in like G Suite, right, when you have enterprise customers, there's an option to allow enterprise customers to encrypt the data with their own encryption key, and then Google never sees the data. So you can send end-to-end encrypted emails, but then you sort of lose some of the features that come with sharing all your data with Google, which is like virus scanning and that sort of thing. So Google sort of has a difficulty giving these features to these particular customers, and they want to grow in that direction. Um, Another thing that I've noticed is as we talk to a lot of people at Google, it's not so much you know the CEO or some director coming down and saying like, we need to like we need to use privacy on our stuff. We need FHE. It's usually the individual engineers working on a product who see what they're doing, and they say, oh, FHE is like a good, like that's the right thing to do for this idea. And they come to us, and it's sort of like Google has this very like bottom up engineer driven culture where the individual like frontline engineers have ideas to like do cool things. And sort of at this point, a lot of the engineers coming to us are saying, you know, privacy is the right thing, right, for this product, and we want to do the right thing. And so it's not just sort of the skeptical regulatory side; it's also the individual engineers who really want to do good by their users. Okay, so why do we need compilers for FHE? So I think there's enough instances of FHE applications that are handcrafted in production settings, and this is good. But Google is a very large company with a lot of products. As I mentioned, Google has lots of legacy C++, and we don't want to rewrite all of that necessarily to be FHE friendly. Um, we certainly don't want to rewrite everything to be like an arithmetic circuit or something, right? So we need a way to sort of retroactively apply FHE to existing code bases without too much additional work. Um, in addition, there's lots of trade-offs involved in FHE, and if we want sort of general purpose applications, then these trade-offs need to be machine assisted or automated in some way, and a compiler is a good way to do that. We have lots of, Google's huge, and we have only so many crypto experts. And so that expertise won't scale across all the people who could benefit it or want to use from it. And we have sort of a lot of abstractions in FHE that we need to manage. So we have this sort of combinatorial explosion of FHE schemes and performance tricks and hardware targets that we need some way to navigate them, right? And a compiler can do that for us. Okay, so why should we use MLIR for a compiler? Right after this, I will get into some of the details of what MLIR is, but basically it is a compiler toolchain. And for starters, many production strength compilers are already built with MLIR. So there's yeah, so it was originally invented at Google for the use to sort of unify the machine learning ecosystem. Before MLIR came along, Google has this thing called protocol buffers, and it was a bunch of like isolated apps that were shuffling protocol buffers around to do various machine learning things. And they decided that, okay, we need to like unify this ecosystem and treat machine learning model training to deployment as like a compiler problem. So they built this compiler ecosystem, or this compiler tool chain called MLIR. And now most of the machine learning stuff that happens at Google is built in some way on top of MLIR, and it's sort of expanded outside of Google. It's part of the LLVM Foundation. And so like I think someone's working on a new Fortran compiler built on MLIR, and there's sort of all these different projects based on it. It's backed by sort of world-class compiler engineers from across the industry. So as part of the LLVM Foundation, it grew out of the LLVM project, which, as you might know, is the backend that Rust targets, is the backend that a lot of modern compilers target. And so there's a lot of very serious compiler people working on MLIR, which makes it a production-ready tool. It also has a bunch of pre-existing tooling, right? The point of using MLIR is that you don't build your own compiler from scratch. So it has all of these debugging infrastructure. It has configuration options. It has things to manage all of the different optimizations and passes. And so it sort of reduces the barrier to entry. And it has a bunch of existing tooling. And so like it has an LSP, it can integrate with VS Code. So it makes it very easy to get started and sort of be productive in it. And sort of the alternative to building a compiler with MLIR is something like, and if you've already written off like handcrafting all of your FHE applications, then there's some like alternative world in which you're building your own language that's just like an FHE programming language. And you could do that, right? I mean, it would also probably involve a compiler or interpreter somewhere along the way. But in general, new languages are very expensive. So at Google's no stranger to building new languages. Here are three of them: Go, Dart, and Carbon. And these three languages each have like 30 or more engineers on them at Google, right? So the FHE team at Google is like 3 engineers. And so we don't nearly have the resources needed to like make a real new production language. And so we have to do something a little bit more efficient. And MLIR is a good fit for that. Okay, so there is a bunch of prior art. So there, in the last couple of years, there have been a bunch of research groups and companies that have been building MLIR-based FHE compilers. And this is sort of a diagram that shows the rough design space of like what your compiler could do. And I don't think I will cover all of the prior art, but just some of them, just to showcase that sort of everybody is tackling sort of a different subspace of this entire chart that we would like to support all of it. So the first one is concrete. So roughly concrete is on the binary FHE scheme side and lowers through LLVM calls to like external calls to the TFHE Rust library. The HECO and HEC8 compilers are doing basically the opposite side. So going through an FHE circuit to the arithmetic FHE schemes and then emitting C API calls to various crypto libraries. I think Seal is the one that people are using. Then there is just like a couple of weeks ago, there was a paper that came out of Beihang University that was also called HEIR. So that was an unfortunate name conflict. But their main contribution was showing that like scheme switching is like a legitimate thing that you can do in production compilers. Like I think this was known, but like not a lot of like concrete use cases in like automated optimizations. So they basically have an MLIR compiler that does scheme switching between, I think it's CKKS and TFHE, to like analyze the different parts of the program. So this is like good news for us because this is also what we want to do in HEIR. And then there is the HEIR MLIR project that really focuses on the bottom end of the stack. So they have like a formalization of polynomial arithmetic, all of the crypto ring math that's needed to do FHE. And they show that you can get a lot of benefits just by having that, doing optimizations at that level and lowering to LLVM and getting all of those optimizations. But as you can see, like there's nobody that handles sort of the whole space, and a lot of these are in some sense research prototypes. So our goal, right, is to we sort of have proven that like every piece of this can be handled in MLIR in some way and provide some benefit, and we want to have a foundation that sort of all of these compilers could use or new compilers could use. That makes it so we don't all have to keep reproducing the same bits of everybody else's compiler in our own hidden place. So, okay, MLIR sounds very great, but what's the catch? So the catch is that we are not compiler engineers. We are mostly cryptographers and application developers. And MLIR is sort of a large, sprawling C++ code base. It's this monolith that is very much nestled in the compiler community. There's lots of jargon, sort of unfamiliar to people in the FHE world. The documentation is well, the documentation could use some work, but also things are changing relatively frequently in the MLIR world. So things are being deprecated, and there's like some parts of MLIR are unstable, and that additionally makes the documentation kind of stale. And okay, so that's a bad thing, right? Because it makes it harder to work with MLIR, but it's a good thing because sort of at Google here we have a lot of our production infrastructure depends on MLIR, and so when MLIR things change, we actually have like an internal on-call rotation, which I am on next week to make sure that things that break in the MLIR external upstream repository don't screw up internal Google stuff. And the HEIR project is part of that. So anytime anything breaks, someone's going to fix it within a few hours, and it will get pushed out, which makes it, hopefully we can protect the rest of the FHE community from the fallout if you're working with this HEIR project. The other catch is that sort of the MLIR community, it's spread across many companies, and there's like everything is the community is somewhat fractured in the sense that people work on what they need in MLIR. So they add stuff that covers what they need, and there's like lots of like missing holes in places that need to be filled in. It's people. I came into the project being like, oh, okay, like I expect everything to just work, right? And like that's very much not the case. And so there's some difficulty that shows up there. And then sort of just like overall in general, right? If I'm aiming for a production strength product, right? Something that's ready to use on like random Google C++, then naturally it's going to be sort of a slower development process than just like some academic paper that you're just trying to demonstrate something. You can assume away a lot of the complexity that shows up in the rest of the world. So that will make it slower. And also, if we want to have a foundation for all of FHE, we need to have sort of the right abstractions that make sense for all of FHE, that aren't just specific to one scheme, or that don't just make this, I think, as my colleague Alex Vian said, we don't want this to just be 3 compilers in a trench coat, right? Just working side by side. We prefer to have some abstractions that work for everything. Okay, so let me get into a little bit of the sort of what MLIR looks like and sort of what it can do. I don't want to dwell too much on the details here because it's sort of like a lot of random source code. I'll have some links at the end for deep dives if you want to go into that. But it's okay. MLIR, it is a software library for building compilers, originally for TensorFlow. Batteries included, so it has lots of predefined optimizations that apply generically to all sorts of compiler problems. And it has lots of backend targets like LLVM and GPUs, and through some misdirection, it can target TPUs as well. And it's extensible. So all of these existing projects, so there's a Fortran compiler, there's a circuit hardware synthesis project, a quantum compiler, and this company called Mojo, and they're all building basically new languages on top of MLIR. So it's extensible, and we should expect it to be extensible for FHE. So it defines, so it stands for multi-level intermediate representation. The intermediate representation stands for like, how does the compiler represent the pieces of a program internally? And it has a, internal sort of data structure representation, but that is translatable to this like textual representation. So you can read the internal like code from the compiler any step of the way. And it looks sort of like what you might expect abstracted assembly language to look like. So you have some variables, you have operations that you can apply on those variables. And then the variables are grouped into things called dialects. So this is a dialect called arithmetic, which handles things like adding, subtracting, multiplying, and comparisons. It has a user-defined custom syntax. So you can basically say, here's what the syntax of my operation in my custom dialect looks like. And you can either, make it look kind of like everything else, or you can write your custom parser and printer for it if you want. And then all of MLIR has like strong stag typing. So you basically have to, pretty much every single instruction needs to know what are the types of the things involved, and that shows up in the textual representation. So this is sort of like what one line of MLIR code might look like. And it also has a lot of like higher level constructions built into the various dialects that it supports. So pretty much everything is a dialect, right? So there's a function dialect that allows you to represent functions and function calls. There is a memref dialect, which lets you represent sort of memory allocations and loading and storing from memory locations in a pointer-based style. There is various dialects that handle different types of loops. So this one is called affine, and affine is a dialect. It's called affine because it is meant to represent polyhedral like loops that are organized in a way that's suitable for polyhedral loop optimization. So that's a whole mouthful, but basically they're saying like, we designed a dialect that makes it easy to do a bunch of important optimizations. And so you will take a program, you will convert, at some point of the compiler flow, you will convert it to this dialect, run your polyhedral optimizations, and then convert it later. And the main thing that this does is like cache locality optimizations. It will rewrite your for loops in different ways so that it's more cache efficient. And then in addition, there are these like existing optimization passes that work on pretty much any dialect, right? So there's something called loop invariant code motion that will take something that is inside a loop that's not affected by the loop, and it will move it up to the front of the loop so that it's only computed once, right? And in order to do this, and in order to have it work in a generic way, MLIR defines what are called interfaces, which are kind of like traits in Rust. There's also something called traits in MLIR, but a trait is just an interface that doesn't have any inputs or outputs. So it's just like a label. And so these interfaces and traits basically allow you to say, hey, this particular instruction is allowed to be moved by this loop invariant code motion pass. And that's called always speculatable. That means that the instruction can be moved earlier than it's actually needed. And then there is something called memory effect op interface that basically says like, does this particular instruction affect memory accesses in any way? And if it does, then you have to worry about like, if you move it, you have to make sure you're not moving it past the memory instruction that might affect it. And there's also like interfaces that say like, this thing looks like a loop. And here's the like information that lets you think, how do you think about it like a loop? And if you implement these interfaces on your custom dialect, then suddenly this loop invariant code motion optimization will just magically work, right? And so that's kind of the idea, is that if you can have all these like sophisticated optimizations, they can work for any dialect, and you just have to, in your custom dialect, you have to add a couple of metadata and small implementations of various functions to enable that functionality. Okay, so so I said intermediate representation. So here, what's multi-level? So the idea in multi-level part of MLIR is that you can have, I guess going back to this previous slide, in this example, right, you have all of these different dialects, and they're doing operations at sort of different levels of abstraction. So you have for loops, you have memref loads, and you have addition and constants. And the multi-level part of the lowering basically says, okay, I'm going to focus on like one particular operation or one particular dialect at a time, and I'm going to take that from its current level of abstraction and lower it to a lower level of abstraction. And that is what they mean by multi-level. It's that you can have your internal representation of the compiler existing at multiple different levels of abstraction at a time, and you're incrementally choosing to lower individual pieces until you get down to machine code. That is, I learned recently that that is like not a completely uncontroversial design choice for a compiler, but this is the one that MLIR has picked. And so as a consequence, they have a lot of infrastructure that makes it easy for you to write what like little rules that do rewrites of different parts of the code base and lowers it from one thing to another, or does like in-place optimizations of things. So one example that here's from one of my tutorials is basically like, okay, you want to minimize the number of multiplications that you do. This is something that people in FHE care about. So you can you can identify some structure that looks like x squared minus y squared, and you can rewrite it as x plus y times x minus y, where you're reducing the number of multiplications by one, right? And this might, maybe there's some cost model you want to use to figure this out, but this is just an example of like, okay, if you want to do some greedy rewrite that just says do these replacements of different patterns that you can find, then you can write them pretty compactly. And you can even do things like add constraints to when the patterns apply. So in this case, this will only apply if x squared and y squared aren't used anywhere else, because if they are used somewhere else, well, then you're not reducing the number of multiplications. You need to recompute x squared anyway. And so this is one way to write one of these little optimizations. There are quite a few different ways to write optimizations. Some of them are like you use a sort of DSL that is provided by MLIR for doing this. And then but for anything like super complex, you basically need to just write C++ code in their infrastructure. So you like subclass some particular C++ class, and then you implement some function that does the implementation of the rewrite using their C++ API. Okay, and in addition to all of these local rewrites, there are all of these sort of global program analysis and global optimization and global cost model things that happen in MLIR. So some of these that do some of the more like impressive things are listed here. So one of them is like taking loops in the affine dialect and turning them into vectorized x86 instructions. Some of them are things like taking two loops that can be merged together into one loop and doing so, or taking two loops that can be split apart and splitting them apart if it makes more sense to do so from a cache locality perspective, doing various loop unrolling and tiling. I know that there's a lot of work that's been done in the FHE community around tiling out of, was it IBM, Intel? I forget. But basically there's a lot of benefit to be had in, especially in the arithmetic schemes, from doing smart tiling, and MLIR already has some of that knowledge built in. Okay, and then this is this sort of increment. This is a taste of some of the incremental lowerings. So of all of the upstreamed dialects, there are all of these little passes that will do just one step of the lowering from one dialect to another. So for example, you can take the function dialect and lower it to LLVM. You can take the the abstract GPU dialect and you can lower it to one of multiple backends to support GPU, like in Vulkan or in SpearV or in, I don't even know what some of these are. You can also do things like, lowering to emitting C API code. So a lot of these lowerings are already built in, but just to demonstrate that there's lots of them. And then here is sort of a diagram of sort of what the, I think this diagram is a little bit old, but it's sort of easy to look at. Okay, not that easy, but it basically shows like, okay, here's all of the dialects that MLIR supports upstream, or the main ones, and the arrows represent different lowerings that are supported from one dialect to another. And so this just shows like, okay, it's kind of a messy web, but you only need to focus on one of these arrows at a time when you're working on some special thing. Okay, so let me switch to talk about like what we're working on in HEIR and why sort of what are the sort of interesting things that are not general to MLIR but are specific to FHE. And yeah, this is a warning that like this project is still very much a young project. Nothing here is finished yet. We don't have any end-to-end compilation flows yet, and there's lots of missing pieces. So I'm describing the ideal that we are working towards and some of the progress we've made along the way. And this is like a very simplified version of the MLIR chart from the earlier slide that shows like what our different flows might look like and what our different abstractions are. So, and this is not like complete or representative of what is actually there, but it's sort of a abstraction. But basically, the idea is that we'll have something at the top that models what it means to have like a secret data type and what secret computation means without knowing about which scheme you're working on. We'll have dialects for each of the major FHE schemes that we support, and we'll have a way to exit MLIR to call APIs like TFHE Rust or Seal from the different schemes that they support. And then we'll have lowerings from the individual schemes to just polynomial math. And that polynomial math, at some point along the way, we will sort of forget we're doing cryptography. We'll just be doing polynomial math and vector math, and then we will optimize those heavily for going through the rest of MLIR and all of the different like cache optimization stuff they have there and affine loops and stuff down to LLVM, or we'll have special support for the different accelerator dialects that we support that, know about FFTs or NTTs, and we'll optimize those particular instructions. Okay, so let's start with the top of this chart. We have we have a dialect called secret, and we would like to do abstracted private computation. So we have a type called secret I32, or we have a type called secret that can wrap any type, right? And so we say, okay, you have a data type that exists like a tensor of I2s or a tensor of 2-bit integers or a tensor of 32-bit integers or a single 32-bit integer. We wrap it in a secret, we call it secret. And then we have a little problem that we want to add two secrets, right? Use it, yeah. Add two secrets in like a generic FHE way where we don't know about which scheme we're using. The problem is that in MLIR, so the upstream arithmetic dialect can't be used because it's not as extensible as I think it should be, right? So you can't just say add I anything you want. If you try to add two things that are in your custom dialect, it will say, well, I don't know how to add these. And there's no way for us to add an interface for that. And I think everyone who's worked on MLIR compiler has for FHE has run into this problem, and most people have solved it by having a like mirror arithmetic dialect. So I think the Zama folks in Concrete, there is a arith or encrypted arith dialect that basically has special data types for encrypted ints and special ops for working on those encrypted ints. And that works, right? You can do that, but it's more work and it's harder to reuse existing MLIR optimizations on that stuff. And so the approach that we're going with is to basically wrap a clear text computation in sort of a secret operation. So this is a lot of code, but at the top here, you'll see it says secret.generic. It takes as input some things that might be secret and some things that might not be secret. And then inside this first line here, this BB0 is basic block. But basically it says you take the clear text version of the secret thing that you have, or if it's not secret, then it just passes through. And then you can just do regular MLIR code on the clear text versions of that secret. And so that represents a secret, a private computation on some data. And then this representation is sort of like the beginning representation. You have your input program, you wrap the entire program, that has secret stuff in it in something called secret generic. And then there's a pass that we have that basically will split that up into individual operations on the individual secrets. So basically it will say, okay, anywhere that you're not actually using secret stuff, I can just like drop the whole framework. But anywhere that you are taking either two secrets or secret and something that's not secret and doing an operation, I'm going to keep that secret generic thing, but I'm just going to wrap the single instruction. And then from there, you can do like a targeted thing where you can say, oh, okay, I have a secret I32 and I'm adding it to an I32. I would like to have my, dialect specific addition operation that adds a ciphertext to a clear text, right? And I will just lower to that specifically. Um, and right, okay, so that's like sort of like our sort of first thing around secret abstracted computation. But there's like a lot more that we need to do there, specifically related to like which keys are you using for the secret, or like is this the right place at which to represent key management, or like if we should we add like a client server abstraction at this level to say like, okay, here is to the client, the thing is not secret, so they can just do plain text computation on it. And so, where should we move some computation from the server to the client, or should we leave it in the server? And how will the cost affect that? Um, uh, okay, and so once you have your secret thing, you'd like to lower it to some particular dialect. So I'll give as an example CGGI, and part of the difficulty that I'm glazing over here is like, okay, how do you take a secret I32 and lower it to CGGI when CGGI doesn't support 32-bit ciphertexts? That is a question that I'm just going to leave to the side for a minute, but it's an interesting one. But once you've lowered to a particular dialect, you have like the typical types of FHE problems where you want to build a circuit, the different operations in the circuit add noise, and you have to figure out like, okay, not only how do I lower an operation in a way that's supported and fast by this particular scheme, but how do I manage the noise if I'm going to like move those instructions around or do it in a different way? I need to make sure that I'm not violating the noise at any step. So we're right now in the process of like actually defining what the scheme dialects look like, and once that's done, then we need to move on to this problem of like how do we model noise, but or how does the noise analysis get into the MLIR? So we haven't gotten to that part yet, but this is a very interesting challenge and a good way for the FHE community to contribute, because there's so much knowledge about the different schemes and the different ways to represent different operations. This is a place where I think the community can really come to help. And then there's the question of like, okay, how do you lower CGGI to poly, right? And this is effectively an implementation of the cryptography, right, in the compiler. And so this is like an example. Here's a blind rotate function, and it has some like placeholders for things that we haven't defined yet, right? This is my sketch of what it will look like. And this is the naive, like, not using any optimizations, just doing the textbook CGGI blind rotate operation. And you can see that like we're starting to lower through normal things like for loops, and there's some polynomial math in there, like defining a monomial and doing a monomial multiplication. And then it still has some operations from CGGI, like doing the lower level CMUX operation with the bootstrapping key piece and everything. So this is just like an example of what the lowering will look like. And then at some point we'll get down to like, at the very bottom of CGGI, right? The core operation is like this big tensor multiplication of polynomials, right? That's either done by FFTs or done by something else, right? So I work on this like TPU implementation of TFHE, and we don't use FFTs. We use tensor. The TPU unit has this like matrix multiplication thing, and so we do it just as like plain matrix multiplication. But the point is that you have like all of these decisions about how to lower it. And those decisions can't really be made unless you really know what type of polynomial ring you're working in, and the details there. So we have this like formalization of what it means to be a polynomial and arithmetic in polynomial rings with particular quotients. And so this is like an example of how you might define a typical setup for like a TFHE. You have your this 1024 is the security parameter for the RLWE problem. You have your coefficient modulus is 2 to the 32. And then you basically can define constant polynomials. You can do multiplication. You can do things like extract the leading term. And then you can even have things like FFT operations on them. And so we have sort of like, this one is a little bit interesting from the MLIR perspective, because the MLIR community has liked this enough that we are planning to upstream it. So the polynomial dialect is going to be an official part of MLIR soon. And that will include sort of the lowerings down to LLVM. And right, okay, so this is probably a little bit gratuitous to the FHE community, but fast polynomial arithmetic is a hard problem. It's largely a solved problem, but in FHE there's a bunch of extra twists in that we can't always use the parameters we want, right? Like, so the choice of the ring is like a security critical choice. If you change that plus to a minus, right, the crypto is broken. The exponent, x to the n, is a security trade-off. The bigger you make that, it has different effects on how to do things quickly. And then there's all of this stuff around the coefficient modulus, right? If your coefficients are NTT friendly versus not NTT friendly, they can be machine word size versus some like multi-hundred bit prime, right? And then you have all these questions with how, like, okay, you may or may not be able to do big integer arithmetic easily on your machine. So there's the RNS trick, and you break it up into pieces. And then the question is, how do you represent that in the compiler in like a sensible way, where you are sort of tracking all of these separate operations together and trying to vectorize them, right? So but more often this is we're not sure how the crypto is going to change in the future, right? So someone might attack RLWE for this particular ring, and we'll have to like change the modules. So our idea with the polynomial dialect is to generalize it, to have not quite any ring, but a large class of coefficient rings, and any ideal generator that you choose of your choosing. So this is basically what we're going to upstream. Okay, and then there's the sort of, to me, the most mysterious part is the hardware dialects, because I'm not a hardware person. But on the LLVM side, I think a lot of that is already solved. There's the vectorizer, there's affine loops, there's x86 and GPU stuff. And so we kind of know that we're going to get some serious benefits on CPU just by going through LLVM and using its optimizer. But we're working with and planning to have HEIR support like per platform hardware dialects. So we're talking to the Aptalysis folks. We'd love to have an optical dialect, right, that targets their optical accelerator. We're working with some folks on FPGAs, and we have our internal TPU stuff. And basically, we're going to have a dialect for each of those that allows you to do the correct representational and optimization choices for that particular hardware backend. And once sort of the FHE stuff is, or once the crypto stuff is gone and we're just trying to do fast polynomial math, this reduces to like a lot of scheduling work. So we're like, this is, I think, what's going to happen at the hardware level is how do you schedule these things efficiently on the particular hardware, and that's going to be like a lot of the work. And once we get this done, right, then we have this like amazing thing where we can do benchmarks, right? We can have application benchmarks that run in different schemes through different optimizations on different hardware, and we can really get like a proper industry-wide set of benchmarks that we can sort of gauge all of the progress in FHE against. So that, I think, is very, very exciting. And some of the like big questions that are coming up, I think I mentioned them, so I'll just cover them a little bit. But this is where like I think answers to these questions can come from the community, and we'll have to like work it out in the compiler. So one of the questions is like, when should the compiler forget we're doing crypto and just do polynomial math? In other words, we want to like keep the crypto information around as long as possible so that we know we can make safe transformations of things without violating noise or anything. And then at some point, we have to just do polynomial math, and then we have to be a little bit more conservative in what we do so that we don't make semantic changes to the program. Another question is like, yeah, how late can we commit to representational details, like how we do our RNS decomposition, or if we do RNS decomposition versus some other kind of like big integer decomposition. What is the right approach to noise models? So how, like, a lot of the noise models in the literature are bounded in some way or another, or taken with expectations in some way or another. Like how precise can we make the noise model be while still being able to efficiently solve optimization problems with respect to that noise model? That's, I think, a very difficult problem. And that's difficult in part because changes to the program will change the semantics of the actual like output, right? Like, and this is particularly true in arithmetic schemes where there's like approximation happening, and you can do like an approximation of a higher level function with low depth arithmetic circuits, right? And and all of this is intertwined with security parameter selection. I remember in Zama's concrete talk, right? That was the big thing where it's like selecting these parameters is this very difficult optimization problem with respect to the noise. And then since we want to do hybrid schemes and cross scheme optimization, right? We want to know like how do you do like data flow analysis through these hybrid schemes? That will be kind of interesting. Um, and then with all of these different performance tricks, there's a question of like what's the right cost model to use at any layer of abstraction, right? Is sort of a big hard question that we'd like to solve. Okay. Just in the last few minutes, part of the difficulty of doing this is that so this is someone I talked to at the last big FHE summit. They said we tried using MLIR, but we found the learning curve too steep. So instead, we built like our own custom compiler from scratch. And so that suggests that there is like this like Venn diagram of people who can read and understand the FHE crypto and people who can implement MLIR passes, and the intersection is not as big as we'd like it to be. So we are engaging with the MLIR community to try and get some of those people more interested in the crypto side. But for this audience, right, I am writing a series of MLIR for beginners tutorials that are like aimed at somebody who knows how to write programs and knows C++, but has never done any compiler work or is not particularly aware of like how compilers work. This is like very low level, like here is what each of the things does, and here's all the generated code, and here's how you connect things together to do like very simple tasks, with the idea of like eventually folding you into the HEIR project. So if you're interested in like diving deep on how to start using MLIR, it's right here. And then on our GitHub, we have a bunch of like open issues that we can start working on, and there's a big discussion thread on GitHub about like what are the choices we should make on the different dialects and all of that stuff. And so please, if you're interested in this, join us. We're a small group at Google and Alex at Intel, but we are around to like answer your questions and help you get started and work on things. So that is all I have, and I think we'll take the last 10 minutes for questions.